All right, welcome everybody to the Properties of Power series video. Thank you for checking in. As a reminder, classes flip for the rest of the semester. You'll watch these videos, and then on different days during the week, you can go in and work on stuff in class and take quizzes where someone will be there to answer any questions that you have as well on the days that are agreed on. So that's that. Announcements, homework, and My Open Math. Make sure you're working on it. Tomorrow is Honorary Friday, so to be clear, whenever you're watching this, Thursday is Honorary Friday. Your Friday classes meet on Thursday. Your Thursday classes do not meet. And then Friday, go enjoy Apple Blossom. Apple Blossom's a lot of fun. Enjoy it responsibly. All right, so let's do that last question from the last slideshow. Again, we're going to use the geometric series here, where, before we had a times r to the n, the sum from 0 to infinity of a times r to the n is a over 1 minus r. And now all we've done is replaced that r with an x. Okay, and I still approach problems that look geometric in the same way that I always do. So let's start writing out terms for this first one. So here, the sum from 0 to infinity of minus 1 to the n times x to the n. Once I start plugging in terms and looking at what we get, it should be clear what kind of geometric series I'm working with. So plug in n equals 0, I get 1. 1 to the 0 times x to the 0 gives you 1. Then the next term is minus x. Then the next term is plus x squared. The next term is minus x cubed plus x to the fourth minus x to the fifth, and so on and so on and so on. This is a geometric series. How do I know it's geometric? Because to go from one term to the next, I multiply by r equals negative x. From 1 to negative x, I multiply by negative x. From negative x to positive x squared, I multiply by negative x. From x squared to negative x cubed, I multiply by negative x. This is a geometric series with r equals minus x and a equals 1. And so the sum n equals 0 to infinity of minus 1 to the n, x to the n, is equal to a over 1 minus r, 1 over 1 minus x, which gives me 1 over 1 plus x. And this is true, or this will converge absolutely for absolute value of r less than 1, but that means absolute value of negative x less than 1, which means absolute value of x strictly less than 1. Now, with geometric series, you do not need to check the endpoints. This is the interval of convergence, and the radius of convergence is therefore 1. You can go into Desmos and check this. Desmos. In Desmos, I type the sum n equals 0 to infinity. I'm just going to, again, use 100 of minus 1 to the n times x to the n. There's the function we're looking at, 1 over 1 plus x. Looks like that. And these agree for absolute value of x less than 1. So it's pretty cool. Geometric series lead to pretty straightforward calculations for functions we can represent using those series. I'll give you all a second to pause the video and try the next question out. Okay, so find the function that this represents. So the first function that we found was 1 over 1 plus x. Take a second and find the function that is representing, that this power series is representing in number 2. Okay. Hope you paused the video. Again, the way I do most of these problems to get us at least start off most of these problems is I start writing out terms. The sum n equals 1 to infinity. So I am starting at 1 here, so be careful of that. Of x over 3 to the 2n looks like. Start writing out terms. I get x over 3 squared. Plus, then the next term is x over 3 to the 4th. Plus, next term, x over 3 to the 6th. There's the n equals 3 terms. n equals 4 term, x over 3 to the 8th, and so on, so on, so on. Okay, this is again geometric. I just need to figure out a and r. Well, a is x over 3 squared. A is the first term. R, to go from one term to the next, is it the case that I always multiply by the same thing? And the answer here is yes. I just am multiplying by x over 3 squared every time. And so this series, the sum 1 to infinity of x over 3 to the 2n, converges to a x over 3 squared over 1 minus r. Now I can simplify that a little bit, right? This is x squared over 9 over 1 minus x squared over 9. And then if I multiply top and bottom by 9, I get x squared over 9 minus x squared. And I can go and look at this in Desmos again. So here's the series in Desmos, the sum from 1 to infinity, which I'm, again, using 100 as a stand-in, of x over 3. Oh, before we do this, hold on. We should also find the radius of convergence. The radius and the interval of convergence happens for r less than 1. So that means x over 3 squared needs to be less than 1, which means absolute value of x, take a square root, over 3 is less than, well, square root of 1 is 1 still, so that the absolute value of x is less than 3. So this is the interval of convergence for this power series. The radius is 3. Let's go verify that. To the 2n. Okay. Here's x squared over 9 minus x squared for x less than 3. Wow, they perfectly line up. Math is amazing. Okay, so that's how you use geometric series to, or how you can find what function a geometric series is representing, at least on the interval of convergence. All right, so let's talk about some properties of power series. I'm not going to prove any of these. The proofs just come from looking at partial sums and going from there. And technically, we've looked at similar properties for infinite series. These are kind of the same idea with a few generalizations going on here. So if f of x is the power series, the sum from 0 to infinity of a(n) times x minus c to the n, and g of x is the sum from 0 to infinity of bn times x minus c to the n. So notice these are both power series centered at c. They have the same center. Same center there. And both power series have a radius of convergence r. Technically, that's a little too strong. You could have f of x and g of x have a different radius of convergence. And in that case, the things that all follow here will all be true on the smaller radius of convergence. Okay. So then f of x plus g of x, I can just literally add the coefficients from f of x and g of x to get the coefficients for the function f of x plus g of x. Okay, so this says for a two power series, if you add two power series together, you just add the coefficients as long as they have the same center. Okay, a constant times the the constant times f of x. If you want to find the power series representation of that, well, you just multiply all the coefficients a(n) by that constant k. And lastly, if I multiply f of x by x minus c to the n, so again, c there is that center for all these power series expansions, then I'm going to get the sum from 0 to infinity of, so the coefficients stay the same, but notice the power on my x minus c, I've literally just distributed the x minus c into the power series. And when you do that, x minus c times the sum n equals 0 to infinity of a n times x minus c to the n. Right, I'm just bringing these in and then combining like terms. This gives me the sum n equals 0 to infinity of a n times x minus c to the little n plus big N. And these all still have that same radius of convergence r that g and f share. And again, that's actually a little stronger than we need. If f of x and g of x have different radii of convergence, then these will all be true for the smaller of the two radii of convergence. So just keep that in mind. It won't come up a lot, but technically that might come up. So one other thing that we frequently do, that we do all the time actually with power series, is if I know the power series for a certain function, f of x, is, and this is a power series centered at 0. If f of x is represented by this power series, it's sum from 0 to infinity of a n times x to the n, it has a radius of convergence of capital R, then if I want to find out the power series representation for f of some constant times x to the k, so I'm plugging something into f. Well, the way I find out that power series for this kind of composition is I literally plug in c times x to the k into the power series up here, right? If I plug in f of c times x to the k into the power series, the sum from 0 to infinity of a n times x to the n, well, I'm plugging in c times x to the k, and then I get this, a n times c to the n times x to the k n. And that's where that comes from. Now, the radius of convergence changes a little bit. And you can see this by looking at the formula that we had for it, that we had for it in terms of the ratio test. But this literally just comes from the ratio test. Okay. I would not recommend memorizing this. I would again recommend using the ratio test to find radius of convergence and interval of convergence. All right. So we can use this in sort of two directions. We can say, I know the power series representation of f is this, and so if I plug into f, then I get this power series representation. But if I am looking for a power series representation of something of this form, we can also kind of work backwards as well. So let's look at this example here. Find a power series representation centered at 0 for the function f of x is x over 2 plus x squared. This, when you look at something like this should remind you of the geometric series. And in fact, the only thing we know how to calculate still is the geometric series. That's the only thing we truly know how to find the actual value of. So let's try and manipulate this so that we're looking at something that looks exactly like a geometric series. Okay, so the geometric series, as a reminder, geometric series tells me that 1 plus x squared plus x cubed plus blah, 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 blah equals, which is the sum from 0 to infinity of x to the n. That is equal to 1 over 1 minus x, okay? So I see something that's kind of similar to this idea, so I'm going to manipulate this until I get something that looks like that geometric series. So first thing I notice differences between what I have here and here are I've got an x up here and a 1 right here. That's not that bad. We can take care of that by recognizing that, hey, this up here is actually our first term, a, right? And if I multiply by a in here, then I get an a plus ax squared plus ax cubed. Okay, so this just tells me that a is x. My very first term should look like x. Okay. The other sort of more annoying thing is that I have a 2 here, where in this formula I have a 1. And then I've got an x squared here, where a plus x squared, where down here I have a minus x. So let's take care of the 2 first. I want to take care of that 2. I want to turn it into a 1 somehow. So what I'm going to do is I'm going to factor out a 2. So I'm going to factor that 2 out from the denominator, and because a constant out in front of a function, we know how that affects power series. That just multiplies power series by that constant. So if I factor that 2 out, I'll be left with 1 plus x squared over 2. All right, so now I have a 1 in that first place in the denominator. That's what I want. But I've got a plus x squared over 2. I want it to be minus blank, right? So what I'm going to do is I'm going to put a minus there. A plus is minus a minus, right? So plus x squared over 2 is the same thing as minus negative x squared over 2. Okay. And now, hopefully, you see that if I call this A and this R, then this is the same thing as 1/2 times, well, A is x, so x plus A times R, so the first term, so x times negative x squared over 2, plus A times negative x squared over 2 squared, plus x times negative x squared over 2 cubed, and so on, right? This looks just like the formula for the geometric series times 1/2. With A is x and R is minus x squared over 2. Okay. And so let's write out what this actually looks like then, comparing to what we have over here. This should look like, well, the sum from 0 to infinity of A times blank to the n, where x is really that common ratio, right? So I'm going to get the sum from 0 to infinity of A times R, right there. Oops, let's write that in black. Times R to the n. And now I distribute that to sort of write things in a simpler way. This is 1/2 times the sum n equals 0 to infinity of x times that minus 1. This is minus 1 times x squared, so I get a minus 1 to the n times, and then x squared to the n is x to the 2n, and I have a divided by 2 to the n. And sort of putting everything in the summation and simplifying, I'll combine my x's. First, I've got that alternating minus 1 to the n times, I've got x here, x to the 2n times x, so that's going to become x to the 2n plus 1. And then I've got 2 to the n here, and then I'll multiply by 1/2, so that will really look like, actually let me write that in red. That will really look like over 2 to the n plus 1. There we go. So let's go and make sure that this works, that this is true. By the way, the radius of convergence and the interval of convergence, we know, just comes from the fact that absolute value of r is less than 1. R for us is negative x squared over 2. We want that to be less than 1. The negative just goes away when I take absolute values, so I get x squared over 2, absolute value less than 1. Multiply both sides by 2, I get x squared less than 2, so I get x less than the square root of 2. That's my, when I take a square root there, it's absolute value of x less than the square root of 2. So that's my interval of convergence. Let's make sure this works out. Let's hide all these things. And then we're looking at first, the function we want is x over 2 plus x squared. Cool beans. And then our geometric series looks like the sum n equals 0 to infinity, but again, Desmos hates infinity, so I'll just write to 100 of minus 1 to the n times x to the 2n plus 1 divided by 2 to the n plus 1. N plus 1. There we go. And we see, again, that this is perfectly lining up. In particular, is perfectly lining up for absolute value of x less than the square root of 2. Boom! Wowee. Amazing. Okay. So again, right now, the only thing you know how to work with is a geometric series. In some form. So if I ask the question, what's the power series representation of a certain function, you try your best to make it look like a geometric series in some way. Okay, you just try to force it to look that way. Amazing. So one of the coolest things we can do with power series is we can differentiate and integrate a function if we know its power series representation. To find the power series of the derivative, we literally just differentiate the power series term by term, which is wonderful because differentiating the power series term by term is the same thing as just using the power rule over and over and over again, everyone's favorite rule. Right? So if you know that the function f of x has the power series representation given here, the sum from 0 to infinity of an times x minus c to the n, and you want to find the power series representation for the derivative of f, well, that just becomes, just use the power rule, right? The derivative of this thing with respect to x, I bring the exponent down, so I get an times x minus c to the n minus 1. Now, something you want to be careful about is when you differentiate the constant term, you just get a 0, and you don't want to say that you get like x minus c to the negative 1. So that's why the index, when you take a derivative, the starting index increases by 1 here. And you get this power series representation for the derivative of f of x, which is pretty cool. Okay. You can also integrate power series term by term, again, just using the power rule. Okay, so if you know the power series of f of x, to find the power series for the antiderivative, or the indefinite integral of f of x, you just don't forget your constant, but then you do the power rule on each term, right? To do the power rule for integrals here, add 1 to the exponent, so you get x to minus c to the n plus 1, and then divide by that new exponent. That's all that's happening here, is you're just using the power rule for integrals on each term individually to get the new power series representation. Okay. And these power series are guaranteed to have the same radius of convergence. They are not guaranteed to have the same interval of convergence. The endpoint behavior might change when you take the derivative or the integral of a function that you know the power series of. So that's something to keep in mind, is that radius of convergence is guaranteed to be the same, but not necessarily the endpoint behavior. That could change, and you need to check that individually. So in particular, if I'm working with a geometric series, I know the endpoint behavior. I don't include either of the endpoints for a geometric series. But if I differentiate it or integrate it for whatever reason, then I need to check the endpoints separately, because then I'm not really looking at a geometric series anymore anyway. Okay. So let's look at these power series. Let's find these power series, and then we'll call it a day. So natural log of 1 plus x. I want to find the power series representation of this function. Next class, we'll look at a different way to do this. So by the way, power series centered at 0. It's always important to state your center. Next class, we'll talk about another way to do this. You can use Taylor series to do this technically. But we can use what we have right now, the geometric series, to actually find the power series of this function. And let's see why. So I don't know the power series of natural log of 1 plus x. But let's take the derivative of natural log of 1 plus x and see what we get. Natural log of 1 plus x, take the derivative, gives me, by the chain rule, 1 over 1 plus x times 1, right? Which is 1 over 1 plus x, which is 1 over 1 minus negative x. And hopefully you recognize that we know the power series representation of that function. This is a, this is r, this is the sum n equals 0 to infinity of 1 times minus x to the n, which is the same thing as the sum n equals 0 to infinity of minus 1 to the n times x to the n. Okay, so I know the power series representation for the derivative of natural log of x. So how could I find the power series representation for natural log of 1 plus x? Take a second, decide what you think the answer is. Pause the video and try and work it out for yourself. Hopefully you decided that the thing you need to do now is integrate both sides. I know the derivative with respect to x of natural log of 1 plus x is the sum n equals 0 to infinity of minus 1 to the n times x to the n. By the way, that has an interval of convergence of absolute value of x strictly less than 1. Cool. So if I integrate both sides, I get natural log of 1 plus x on the left. On the right, I get some constant, which we'll be able to figure out in a second, plus the sum n equals 0 to infinity of, all I'm doing is integrating using the power rule term by term. Okay, so the integral with respect to x, I'm going to get x to the n plus 1 over n plus 1. And that minus 1 to the n just comes along for the ride. So as natural log of 1 plus x, we have found a power series representation. We actually need to figure out c, though. The way we figure out c is by plugging in x equals 0 on both sides, plugging in the center. If I plug in x equals 0, I get natural log of 1 on the left. On the right, I get c plus, when I plug in x equals 0, everything's 0 in the actual power series. So I get c is natural log of 1, but that's just 0. Okay. And so this tells us that the natural log of 1 plus x has a power series representation of the sum from 0 to infinity of minus 1 to the n over n plus 1 times x to the n plus 1. Now, the radius of convergence is still guaranteed to be 1. It has the same radius of convergence as the geometric series we worked with originally. But the interval of convergence might not just be -1 strictly less than x, less than 1. So we need to check the endpoints. If I plug in the endpoints, x equals -1, I get the sum n equals 0 to infinity of -1 to the n times -1 to the n plus 1 over n plus 1, which is the sum n equals 0 to infinity of just -1 over n plus 1, which diverges by the divergence test. Or sorry, not the divergence test, because this is the negative of the harmonic series, and the harmonic series diverges. Okay, so I don't include x equals -1. Do I include x equals +1? Well, let's see. Sum from 0 to infinity of -1 to the n times 1 over n plus 1. Yeah, this converges. This converges by the alternating series test. And so what does it converge to? Well, it has to I plugged in x equals 1 on the right. So it has to converge to what I get when I plug in 1 on the left, natural log of 2. So I finally showed you guys that that's where that comes from. Okay. So I can look at this in Desmos again. The sum n equals 0 to infinity, 100 or 1,000 of minus 1 to the n over n plus 1 times x to the n plus 1. There we go. And here is the natural log of 1 plus x. There we go for negative 1, strictly less than x, less than or equal to 1. Okay. And there we go. And we can see that the power series, again, I stopped at n equals 1,000. If I could go fully to n equals infinity, then we would see perfect convergence here. But you can see that the power series does seem to be converging at x equals 1. All right, so take a second, pause the video, try out number 2. Same idea. I don't know the power series for arctangent of x, so maybe take a derivative and see if you know the power series for that thing. Pause the video and try it out. All right, so let's look at the second one. Arctangent of x, we want to find that power series representation. So again, I don't know the power series for arctangent of x. And integrating arctangent of x is actually not that difficult if you use integration by parts, but taking a derivative is much easier. I know that the derivative with respect to x of arctangent of x is 1 over 1 plus x squared. And ooh, doesn't that look like a geometric series? Yes, it does. It looks like a geometric series formula with a equals 1. And r equals minus x squared. Okay, so apparently the derivative with respect to x of arctangent of x is the sum n equals 0 to infinity of a 1 times r to the n, which looks like the sum n equals 0 to infinity of, always break that negative 1 off into a negative 1 to the n, so that you can just deal with, later we're going to take an integral and I don't want to have to use technically a u substitution or anything like that. So I break that minus 1 to the n off, and we have something that looks like this. This is the power series for the derivative of arctangent of x. So if I want the power series representation for arctangent of x, again, we're going to take an integral. This tells me that the power series for arctangent of x, centered at 0. If you center it somewhere else, you get a different looking power series. But if centered at 0, we get this. I integrated on the left, the integral and the derivative undo each other. I don't want to forget my constant, so some constant that we'll figure out, plus the sum from 0 to infinity of minus 1 to the n. I'm integrating with respect to x, so minus 1 to the n, that's just a constant with respect to x. The integral of x to the 2n, that's x to a power, so I'm going to do x to the 2n plus 1, and then divide by 2n plus 1. There we go. Now, to figure out c, again, plug in the center. With power series, you're always plugging in the center to figure out what's happening with respect to constants. Okay, so if I plug in the center, plug in x equals 0. On the left, arctangent of 0 is 0. On the right, I get c plus a bunch of zeros. Everything has at least an x to a first there. And so I get c plus a bunch of zeros. So that tells me c equals 0. And the power series representation for arctangent of x is the sum n equals 0 to infinity of minus 1 to the n over 2n plus 1 times x to the 2n plus 1. Wow. And as a reminder, the radius of convergence for this power series is 1, so the radius of convergence here is 1. But the endpoint behavior might be different. So we need, if we want to find the interval of convergence, we need to look at the endpoints. So the interval of convergence, it has a radius of convergence of 1, centered at 0, so we need to figure out what's happening at the endpoints, right? Plug in x equals minus 1. And we get the sum n equals 0 to infinity of minus 1 to the n over 2n plus 1 times minus 1 to the 2n plus 1. There we go. And let's think about what this looks like here. Minus 1 to the 2n plus 1. 2n plus 1, if n is an integer, that's always an odd power. So minus 1 to the 2n plus 1 is just the same thing as minus 1 to the 1, right? It's minus 1 to an odd power, which just leaves me with minus 1. Okay, so in the end, this looks like the sum n equals 0 to infinity of minus 1 to the n times minus 1 over 2n plus 1. That's the sum n equals 0 to infinity of minus 1 to the n plus 1 over 2n plus 1, which converges by, take a second and think why it converges, the alternating series test. So that converges by the alternating series test, so I can put a bracket right there. Okay. So this series converges at x equals -1. Let's check at x equals +1. The sum n equals 0 to infinity of -1 to the n over 2n plus 1 times +1 to the 2n plus 1. But that's just 1, that 1 to the 2n plus 1. So this gives me the sum n equals 0 to infinity of -1 to the n over 2n plus 1. And that converges by, that's right, the alternating series test. Okay, so this is an interval of convergence that has both endpoints included. It's a closed interval of convergence. This is kind of the first time we've seen this. And generally, integrating will get you a little bit better interval of convergence in the sense that you might see one of your endpoints included from sort of the original power series. But let me go in here and let's look at these power series. Let me get rid of some of these so that we're not bogging Desmos down. Arctangent of x, there it is. And specifically, we care about this for absolute value of x less than or equal to 1. Here is the sum n equals 0 to infinity. Again, I'm just using 100 of -1 to the n times x to the 2n plus 1 divided by 2n plus 1. And there you go. We get convergence on the interval that we're looking at. And this is a cool time to point out that arctangent of 1 is pi over 4. And so this gives us a way to calculate pi over 4. So if you've ever wondered, how do people actually calculate pi over 4? Do they just draw really precise circles and measure the circumference and the diameter and divide? No, that's not how we do it at all. We know that arctan of 1 is pi over 4, but arctangent of x, the power series converges at x equals 1. So I can also use the power series to evaluate this value here, right? This should be the sum n equals 0 to infinity of -1 to the n over 2n plus 1, which looks like 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11, and so on and so on and so on. Okay. And so if you've ever wondered where does the value of pi come from, this is one way to calculate it. Now, this is an incredibly slow way to calculate it, just so you know, because by the alternating series test, and specifically the remainder for the alternating series test, the remainder for this alternating series just looks like the next term, right? So the remainder is no bigger than the next term because we're looking at an alternating series. So with what I have written down, the remainder is no bigger than 1 over 13. But then if I want to use that to calculate pi, I'm going to multiply everything by 4, including the error. Okay, so the biggest error I can expect when I use this to calculate pi is 4 over 13, which is about 0.3. So even going to the 1 over 11th term, the biggest the error could possibly be is 0.3. I still probably won't have 1 decimal point of accuracy. But let's look. Sum n equals 0 to, that's the 0, 1, 2, 3, 4, 5. The n equals 5 term, minus 1 to the n, divided by 2n plus 1. There we go. And if I multiply that by 4, you can see that, oh, that's not very good. That's not a very good approximation of pi. But if I increase the number of terms I'm using, then generally I'm going to get about 1 more decimal place of accuracy for going 10 times the number of terms that I'm taking, right? So here's pi. Why won't you round it for me, Desmos? Well, anyway, you can see 3.1415926.5 should be the next digit. Okay, so again, this isn't converging to pi, but incredibly slowly. Wow. All right, let's look at one more slide. And we're not going to do anything with this necessarily, but I just want to point out the power series representations for a given center for the same center are unique. Okay, and what I mean by that is this: if f of x is the sum from 0 to infinity of an times x minus c to the n, so there's a power series representation for f of x. And g of x is the sum from 0 to infinity of bn times x minus c to the n. So that those power series have the same center. If they have the same radius of convergence, then f of x equals g of x on their interval of convergence if and only if all the coefficients match up. Okay, so if all the coefficients are the same, then you're guaranteed that f of x and g of x are the same thing. Okay, so if an and bn are equal. Now, this doesn't have to be true if you're looking at different centers. One function can have different power series depending on the center that you're looking at. And we'll look at that later. However, if two power functions have the same center and all the coefficients are the same, then they represent the same function. And in fact, you might say, yeah, duh. But it's worth pointing out. It's worth pointing out. And the proof is actually not so trivial. But it is something to note. So that's it. Thank you for watching this video. Next time we'll talk about Taylor series, which is how it answers the question of, okay, so now we know how to find power series for things that are related to geometric series, either through integration or differentiation or multiplying or addition or whatever. That's not all the functions that have ever existed. How do I find power series representations for like sine of x, for instance? And the answer is going to be by using Taylor series and using a pretty formulaic method. So we'll talk about that next time. Thank you all for watching this video. And as a reminder, Thursday of this week, hopefully the week you're watching this, is Honorary Friday. So your Friday classes will meet on Thursday, May the 1st. Okay. All right. Thank you, everybody, and have a great rest of the day.